So in this section, we're going to look at matrices and vectors for the context of holding basis vectors in the matrix. And we're going to look at using the delta basis vectors. So these are the simplest possible basis functions or basis vectors that we can use. So all of the mathematics will actually be very simple indeed, but the methodology is fully general for other choices of basis vectors that we can come across, such as the Fourier basis vectors later on. So let's press on. What we're saying then is that a signal of interest, some kind of discretized function, such as x of n, which I've shown could be, for example, something like this audio signal used in digital signal processing, for example. We're saying that that function can be expressed by using a set of differently shifted delta functions. So here we're saying x of n is equal to a delta function located at -2, that's this one here, and with a coefficient given by the function value evaluated at that index -2. And so we've been through this before, it's very similar to what we've already seen. You just keep going through. So for example, this one here is the delta function located at the origin, and that has a coefficient given by the function evaluated at the origin, so x of 0, all the way up to this example here where you've got a delta function, delta n -2, so that's shifted it 2 to the right, and then this one has a coefficient or a scaling factor of the function evaluated at that position 2. So we go here, x of n evaluated at position 2 is this negative value, and so that's why we get that result there. So that is all summarized by this expression, where we're saying that we can recreate or synthesize a function by taking delta functions, delta n, shifting them to every single location within that function x of k, as shown here, and then using the function evaluated at each of those shifted locations as the scaling or the coefficient, the weighting factor for that delta function, and summing them all together to synthesize our overall function x of n. And so what we're going to do now is take those shifted delta functions and place them inside a matrix and use them as a basis. So we'll see that in the next slide. So here now we can see that we have a matrix of basis vectors, and these are those delta basis vectors or delta basis functions that we just saw in the previous slide. So you can see here I've got the delta function centered at an index of 0, and so that's 1 and then all zeros just stored in that column of the matrix. And then I can shift it along, and then that's the next column, shifted again, that's the next column, shifted again, and again. And so you can see that for this simple case of just having 5 samples in a signal, I can use a basis matrix, we'll see how it's used in a moment, that's just composed of 5 shifted copies of that delta function or delta basis vector, if you like. Okay, so what we're trying to say then is that we can represent any function, any signal x in terms of a weighted sum of those basis vectors. So we're going to be finding, or in this first instance, we're going to be using a coefficient vector c to weight each of the columns in that basis function matrix to reconstruct or to synthesize that original signal stored in a vector x. Okay, so c is the vector of coefficients, and then I'm just making the observation that you should have noticed here, of course, that this basis matrix here is in fact just the identity matrix. Okay, it's just I, that's the notation we normally use for the identity matrix. It's just a diagonal of ones. So the trivial, very simple case, and it does mean that for this equation to hold, the vector of coefficients is going to be just the vector x, and we've already seen that in the previous slide. It's just that the methodology that I'm going to go through in these few slides is, as I say, general and applicable to other choices of orthogonal basis matrices B. Because they could be, for example, it could be the Fourier basis matrix, which would be probably the most useful case going on from here. But just to keep going with this very simple example, this is what happens then when we're now going to demonstrate how to do x equals bc. So b is the matrix holding those delta basis functions, basis vectors, and c is the vector of coefficients. So I've got a coefficients here for those delta functions stored in that coefficients vector c, and I'm just showing how we'd go about finding that output vector x. So that first column is just the delta function centered, just located at that first sample point, which we're indexing by 0. We're labeling these 0, 1, 2, 3, 4. Okay, so this is position 0 here. And so that first delta function, if we're going to represent this example function here, or in this case, use these as coefficients to generate x, and we know that's going to look the same as c. So we just take the first value of these coefficients and use that as a weighting factor for that, that column, and then we're going to place that into the output. So that's what I'm showing there. I'm just showing that if we chose 4 times that column, then we get a 4 here, and all the rest would be zeros. So there we go, the coefficients vector c evaluated at the first position, which I'm using 0 here, and using that as a weighting factor for that delta vector that was stored in that first column. Okay, and so we carry on. So we shift the delta to the next position, so that's 0, 1, and then all zeros, and we've got the next coefficient in the series of 5 coefficients located in that coefficient vector c. Remember, we're doing x equals bc. So this is a scalar value of 5, that second element in this vector, and that's going to act as a weighting factor or weighting for this second column, and then we place that into there, and that's going to give a value of 5. And then of course this is carrying on adding to what we saw in the previous slide. So we've still got the 4 from the previous slide, from the first column, and now we've got 5 coming from the weighted second column. So there we go, that's the coefficient vector, the second element along, because we're counting from 0, and that's the weighting factor for the shifted delta, so delta n minus 1, which is just that column. And so we carry on. So the third element into the coefficients, that's now a weighting factor for that third column. And so we take 3 lots of that column, and sure enough, that gives us a value of 3 in the output vector x, which we're slowly building up here column by column. So now we've got a 4 from the first slide, 5, and now this slide we've got a value of 3. And so there we go, c, the coefficients vector for the third index, again counting 0, 1, 2, counting from 0, as a weighting factor for the delta n minus 2, which we've stored in that column. Okay, now I'm going to the fourth element in the vector of coefficients, and so that's a value of 2, and that acts as a weighting factor for that column. And so that's going to deliver a value of 2, because it's just 2 times that column vector, so it's a 2 there. And of course, not forgetting all the previous ones we've been adding on, that's why this vector is now developing. And so I'm showing there as well, it's just that value, which is the fourth element, which I'm indexing by 3 here, counting from 0. So c at that index as a weighting factor for the delta function shifted by 3. So this is the delta function here stored in that column vector, shifted by 1, 2, 3. Okay, and so the final one is obvious. That's just a weighting factor of 4 for that final column vector, and that gives us a 4 there. And then the overall expression that we have is to say that we can recreate the signal x by taking a summation over all of these coefficients, c, and then the coefficient vector c is accessed by this index k. It's just sliding through the positions in that vector. And then each one of them is acting as a weighting factor for the delta function, which is shifted to the location of each one of those values, each one of those samples in that coefficient vector c. Okay, and so there I've just put up a reminder that this output vector is x, which is equal to bc. So b is just that matrix of basis vectors, and c is the coefficient vector. And then I'm just pointing out again that for this rather, well, the simplest possible case of choice of b, because that's the identity matrix there. When we're using the delta basis functions like that, then that vector of coefficients, when used with the delta functions, will just deliver the same function on the other side here. So we could either use c there and c there, or we could use x there and x there. It would be the same because it's the identity mapping. But here the main point was to show the general concept of using a vector of coefficients with a basis function matrix where the basis functions are stored in columns of B, and then we weight them, sum them all together to get the output vector x. And so just to note then that we don't have to use the notations that I was using in the previous slides. In general then we're going to be, say, reconstructing or synthesizing some signal f, which is just a set of sample values. So it could be, for example, a time activity curve for a PET image analysis in PET imaging, or indeed it could be an audio signal in DSP. Whatever your application for your signal, you've got some series of values stored in that column vector f, and we're saying that we can create that by using a vector of coefficients c as weighting factors for all of the columns in some basis function matrix. We've been looking at the delta basis functions, but again, it's very useful to understand that for when we consider more involved basis functions, such as the Fourier basis functions. And here I'm just representing that matrix vector multiplication in a more conventional kind of discrete function format. So what we're seeing now is that the coefficients vector c is effectively this function here. So we've just got a function value accessed by different positions x prime. And then what we're doing is taking a delta function, delta x, shifting it to x prime, in other words, to the location of each of the values within that function f. And when we do that, this acts as a scaling factor for that delta function that's been shifted to the respective locations, and we sum them all up to get the function on the left-hand side. And again, with delta functions, it's trivial because f and f are just a direct match. So that was matrix vector notation. This is like the discrete function notation. And then at the bottom of the slide, I've shown the continuous domain version of those expressions. So really, we're saying that, again, any function f of x can be expressed as a weighted set of delta functions, where the delta function, so that's delta of x, is shifted to the position x prime here, that we're considering for any particular function f. So we take the function f of x prime, and that gives us a weighting factor for the delta function shifted to that location x prime, and we repeat that for all the possible positions x prime. So when you see this integral like this, that's basically saying, and with a dx prime, that's basically saying visit all the possible x prime positions from minus infinity to plus infinity in that function f. So we slide x prime from minus infinity to plus infinity. At each particular value of x prime, we get a function value f, which acts as a scaling factor, a weighting, or a coefficient, if you like, for the delta function that is actually also shifted to that current x prime that we're considering in that range of integration. And if you do that, then you just recover that function back when we're just using the delta function like that. So as a note there, that is effectively a convolution of this function f with the delta function. And of course, if you convolve something with a delta function, then you just get that function as the output. There's been no change there at all. Okay, so that's how we use a vector of coefficients with a basis function matrix to create an output signal, to synthesize an output vector, if you like. Now we're going to say, well, what if we still had that expression, so x equals bc? So what I've just talked you through is using a known coefficient vector c with a known basis function matrix b, and I've shown you how you calculate x. But now what if we had x and we want to find what are the coefficients for that set of basis vectors that will create our chosen x. So that's what I've written here. How would we find the coefficient c for a given basis set of basis vectors stored in a matrix B that when we weight them all together would recreate or synthesize our original signal x. Now again, with the delta basis vectors, this is a very trivial problem, but again, I'm presenting it to you because of the general methodology applies when we use different basis vectors. Okay, so here we are then, this is the familiar expression. We're saying how would we find the coefficients for these delta basis functions which would create our chosen x. Before we were finding x when given c, now we're saying given x, what would c be? Okay, so to do that then, the first observation I'm going to make is that this matrix B is a special kind of matrix because it's what we call an orthogonal matrix. There's a lot more I can say about orthogonality, but if for the moment you're just willing to accept this definition, which is that the inverse of the matrix is given just by the transpose of the matrix. Okay, so that's definitely not true for the majority of matrices, but there are special special matrices for which this does hold. In other words, the inverse of the matrix is given just merely by its transpose. And you'll see why we need that in a moment, because what we're saying is that our signal x is given by coefficients operating on some basis function matrix B, but we're trying to find those coefficients. So how are we going to find the coefficients? Well, we're going to obviously invert that set of equations. So to find that, we would apply the inverse of that matrix B. So you can imagine we did that on both sides. So inverse of B, that would be B minus 1 operating on X. Inverse of B on B would just give the identity, provided that it has an inverse. And of course, with these kinds of matrices, these orthogonal ones, it does have an inverse. And so therefore, we can find the vector of coefficients C by applying the inverse of the matrix B onto the signal or function x that we're wanting to express in terms of that basis. In other words, it will give us the coefficients if we do this. And because the matrix B is orthogonal, then we have the luxury of being able to find the inverse just by the transpose. Now the transpose means you just interchange the rows and columns of the matrix. So really very, very simple to find. So let's take a look at that. Here's our basis function matrix. It's got columns of the delta basis functions. So we take the first column and we place that as the first row of B transpose. Second column goes to the second row, third column to the third row, fourth to the fourth, and the final column goes to the final row. So this is our inverse of B, because B is orthogonal. So let's see that in action. Now we've got some vector x, that's the signal or function that we want to find the coefficients for. In other words, find the coefficients of those basis vectors that would be able to be used to synthesize x again. So x is now my input here to this B transpose matrix in the middle there. And we're saying, how do we find the vector of coefficients C? So first of all, I take the signal I want to decompose, or rather the signal I want to find the coefficients of those basis functions for, put that signal in as this vector, column vector here. And then, as we've seen from the previous slide, now I've got a row as a delta basis vector. And then obviously I can find the first coefficient for the first delta basis function just by taking this vector in scalar or dot product with that vector. Okay, so the first coefficient is just the delta function multiplied point by my function of interest, and then I sum up the result. Okay, and now we know that for the special choice of delta basis, that's going to give us x0, but in general, it's going to give us the coefficient, okay, for other choices of basis. So that's a very simple process. We're saying take the signal that you want to express in some other basis. What you do is you multiply that signal, that function, by the basis vector. And once you've done the multiplication, you get some output here. And then you sum up the result. And that will give you the coefficient for that particular basis vector that would go into resynthesizing your signal x. Now here, of course, with the basis vector, it's just the trivial outcome of being equal to x0. But this expression here is the key one. We're saying take that scalar product, in other words, multiply the two functions together, multiply point by point the two vectors together, and sum up the result. And so we would go on. That's how we'd get the second coefficient. We'd now slide that delta function to the next position. So there it is there in that second row. And we'd multiply it point by the function x, or the vector x that we're wishing to find the coefficient for that particular basis vector. Multiply it point by point. So here that's exactly this expression here. So we've got the delta function shifted to that particular position, because that's the basis function that we're trying to find the coefficient for. When you've got the basis function, you then multiply it point by the signal x, and then you sum up the result, and that will give you the second coefficient, which again, for the trivial choice of the delta basis, is just going to be x1 in this instance. And so we could carry on. So I'm just showing here a more general case of this row here. If we wanted to find that coefficient, then we'd take that row of the matrix B transpose and multiply it point by the input vector x. Okay, so the delta function, delta k, shifted to position n along there. So in this case, that's 0, 1, 2, 3. And then that would be, that function is then multiplied point by this function, okay, this vector. And then you sum up the results, and that will give you the amount, in other words, the coefficient of that basis function that is present in the signal x. And again, I'm making the observation that when using delta basis functions, then the outcome here is just x, okay, because this is just the identity matrix. This is also known as the sifting property of the delta function. So to understand that, what you can view this as is a delta function, delta as a function of k, it's then shifted to position n. Okay, that's the kind of thing we're seeing here. A delta function, delta of k, shifted to position n in that independent variable, and then it's multiplied by x of k. And so that multiplication would mean that that one there would pick out position n. So imagine it's this case here. So imagine it's this sample. So if the delta function is shifted to here, it then gets multiplied. That gets multiplied point by this function, this vector. And so it will just pick out that value there, because obviously elsewhere to the left and right of that delta function we have zeros. So all of those go to zeros, and it just leaves that value there. Okay, so when we do the summation, again, we still only pick up that value, and it means we get the function evaluated at that index position n. So the sifting property says take a delta function, shift it to position n, multiply it by the function, sum up the result, and you get the function evaluated at that position n. Okay, so to summarize, begin to summarize what we've just talked about then. For the discrete case, we're saying we can express a signal, a function, or a vector as a weighted sum of delta functions or impulses in sort of temporal systems, or point sources for spatial imaging systems. So we can express x as a weighted sum of delta functions, okay, where the weights are given by some coefficients, c, which as we know, for when we're using delta basis functions, it's just the same as x, but again, the principle is general. So we can express a signal as a weighted collection of these basis functions, okay? And so that takes us right back to that very first slide I started with. And then conversely, if we're no longer doing the evaluation, but we're saying, well, no, I've got a signal x and I want to find the coefficients of some basis for that signal, then what you do is you take the signal, you multiply it by the particular basis vector for which you're trying to find the coefficient, and then you sum up the result, and that will give you the coefficient for that particular delta function. Okay, and then those equations which I've just written for the discrete case can also be written for the continuous case. And so here we're saying that, that some function f can be expressed as a weighted collection of delta functions. This is the delta function in the continuous case. And all we're doing is shifting it to every possible x prime position within the original function f. And then we're just treating the function f as a scaling for that delta function for every single location that it's moved to. Okay, so just imagine sliding a delta function from minus infinity all the way up to plus infinity in every single position. We then multiply it by the function and integrate, and that's going to give us the function evaluated. It's going to give us the same as the function, basically. And then likewise here, this shows us how to find those weighting factors for those delta functions. And really all we're saying is just take a delta function, again, slide it to the position, multiply it by the function and integrate. And that will give you, so here you can see a delta x prime is being moved to position x, and then when we multiply it by the function and integrate, it just picks out the function value f at position x, and position x is where that delta x prime had been shifted to. So that's known as the sifting property of the delta function. And it's an observation really that these two expressions are in fact equivalent because the delta function is an even function. You'll have noticed that x minus x prime, delta x minus x prime, is equal to delta and then minus of that argument. So x prime goes to plus x prime, x goes to minus x. So all I've done here is just negate the argument of the delta function, which you can do, and it's actually equivalent for the delta function because delta x is equal to delta minus x. So therefore, delta x minus x prime is equal to delta x prime minus x. Okay, so in review then, we have a matrix holding basis vectors or basis functions, and then we can understand matrix vector multiplication using those two methods that I've been through, and then I've just related those descriptions to the continuous description. Thank you.